Okay, so today we're going to talk about section 1.8 of Anton, and this is about matrix transformations. So a transformation is a function or a map, those are some other words for it, and it takes something as input and gives an output. So this is similar to what you might have seen in pre-calculus of a function. A function takes a number as input and gives a number as output. But in this class, the inputs will not be just necessarily always single numbers, but what are called n tuples. That means an ordered list of n numbers. Here I've represented the numbers by variables, x1, x2, xn, just like in calculus or pre-calculus you might represent a function as f of x. X represents the input. Okay, and then the output of our transformation will be an m tuple. M is going to be some number. In other words, just a list, an ordered list of m numbers. And our book tends to use w as the letter for the output variables. Sometimes in pre-calculus or calculus, you use y for the output, x for the input. Our book tends to use x for the input and w for the outputs. Now, just a piece of mathematical notation, r, written like so, denotes the set of real numbers, and our book just uses this regular r. Mathematicians tend to write this form of r in their papers and on blackboards. And then Rn, r raised to the n, is the set of n tuples of real numbers. So for example, r cubed, or r to the third power, is x1, x2, x3, the tuples of three tuples, a list of three numbers, and where each number is a real number, is an element of R. So this is what this backwards looking E or epsilon symbol means. It means, or is read as, an element of. So we say that the 3 tuple 1, 0, negative 1 is an element of the set R to the third power, or r cubed. Another element is 0, 1, minus 1. And then very often throughout this book and course, we'll write n tuples not as an ordered list horizontally, but as what's called a column vector. In this case, 3 by 1 column vector. So this 3 tuple, or element of R3, corresponds to this column vector. And we'll see why we're using column vectors on the next slide. So the goal of this section is to introduce what's called a transformation. And I want to illustrate this by an example. So I have a matrix A here, and I've just made a random example. This is a two rows, 3 columns, so it's a 2 by 3 matrix. And it defines what's called a matrix transformation. And again, a transformation is you give me something as input, and I have to tell you what the output is. So the input is usually denoted with x's. And so given this column vector as input, we treat it as an element of R3. Again, it's just a list of 3 numbers. And then here's the definition, and I'll have to explain it. You give me this column vector x here as input, and the output is the matrix multiplication of A, this matrix A, times x, this matrix x here. Now, in other words, this transformation, and our book denotes T sub A, where A is the associated matrix. Again, here's just one specific example of such a matrix. For every matrix, there's an associated matrix transformation. And that takes as input elements of R3 and gives back elements of R2 by matrix multiplication. And our book is using W to denote the output. Now we have a 2 by 3 matrix here, and a 3 by 1 matrix is our column vector here as our input. And when we multiply them, well, first of all, we are allowed to multiply them because the numbers here match up, 3 and 3. And then the output will be a 2 by 1 matrix. So that's why I've written W as a 2 by 1. Again, 2 rows, 1 column. All right, and so then here on this side, I've done the matrix multiplication. I made a matrix, and it's going to have 2 rows. Here's the first row, here's going to be the second row. And let's go through how I found this first row. This is row 1, column 1. So I take row 1 of the first matrix, column 1 of the second matrix, and take their quote-unquote dot product. 0 times x1 plus 1 times x2 plus 1 times x3. That's exactly what I've done here. And when you simplify that, you get x1 plus x3. Now in this position here, this is row 2, column 1. So I take row 2 of the first matrix, column 1 of the second matrix, and take their dot product. So 2 times x1, that's here, plus 1 times x2, that's there, and 0 times x3, that's there. And then when I simplify that, I get this. So that's our output, which we denote using W with a vector or W1, W2. And so this 2 by 1 matrix column vector W1, W2 equals this 2 by 1 matrix. And in other words, W1 equals x2 plus x3, W2 equals 2x1 plus x2. So that's what our transformation T sub A can also be written as this collection of information. And let's actually plug in some numbers to see what's happening. So for example, if x1, x2, and x3 are 1, 0, minus 1, in other words, x1 is 1, x sub 2 is 0, x sub 3 is minus 1, then our transformation T sub A for this specific matrix A takes these as inputs and gives this as output. Now, how did I find that minus 1, 2 is the output? Well, it's done on the next page, but also here you can see that W1 is x2 plus x3. Here's x2, here's x3, and we add them. 0 plus negative 1 is negative 1. And then to find the W2, or what number that goes here, I take 2 times the x1 and add x2. So 2 times 1 plus 0, and that's simply 2. Now, another way to find that answer, and the way I normally do this, I suppose, is simply do the matrix multiplication. Here we have our matrix A. Here's our specific input vector from the previous page, and this transformation is simply multiplication on the left by this vector A, by this matrix A. And so when you do the matrix multiplication, so again, row 1, column 1 is what's in the row 1, column 1 position here. I get minus 1 when I do the arithmetic. And then similarly, row 2, column 1 is in the 2, 1 position here. And I get this, the same answer we got before. And so that's what this transformation does. It takes this as the input vector and gives this as the output vector. And then as a reminder, when you transfer vectors to tuples, now these tuples have round brackets, not square brackets. So that's the slight difference between column vectors or even row vectors and tuples. Okay, so this T sub A for our specific value or matrix A takes 3 tuples, 3 numbers, as input. That's sometimes called, the domain is called the input. That's a mathematical term for the input, the set of inputs. And then the codomain is the mathematical term for the set of outputs, or I should say the set where the outputs live in. And in this particular example, the outputs were a pair of numbers, an ordered pair of numbers, so a 2-tuple, or a 2 by 1 column vector. And I circled these, or it's not circled, boxed these 2 exponents here to indicate a general phenomenon. In our case here, A is a 2 by 3 matrix, and it took a 3-tuple as input and gave back a 2-tuple. And a general fact that's easy to see is that if A is an m by n matrix, in other words, if it has m rows and n columns, then the transformation that's given by left multiplication by A takes an n-tuple, or an n by 1 column vector and returns an m tuple or an m by 1 column vector. A simple example or exercise is on page 82, number 2. It says A is a 4 by 5 matrix. Find the domain and codomain. And the answer is, well, this is a 4 by 5 matrix, and so for inputs, you will be giving a column vector with 5 rows. In other words, an element of R5, so that's the domain, and then the codomain is R4, because when you do the matrix multiplication, you'll be multiplying a 4 by 5 matrix by a 5 by 1 matrix, and you'll end up with a 4 by 1 column vector, which is an element of R4. Okay, now let's go backwards. Suppose we were given a linear transformation where the outputs were W1 and W2 and were given by such formulas. What is the associated matrix? Okay, so then we notice that here we're requiring 3 variables, x1, x2, and x3, and so the domain is going to be R3, the input. Again, domain stands for the set of inputs. And then the codomain or output is W1 and W2. Those are their variables representing the output. And so the codomain is R2, because you need 2 numbers to describe an element of the output. And so our transformation is going to go from R3 to R2. So our matrix A is a 2 by 3 matrix, and one can discover, as I'll show shortly, that the corresponding matrix is this. There's a couple ways to do this. One is if you kind of stare at what's going on, you see that the coefficient of W1 is 0, 1, 1, and so that's the first row. Coefficients of W2 are 2, 1, and there's a 0 on the x3, so that's the second row. You find the answer, and that's going to involve what are called the standard basis vectors, and we'll see these throughout the course. So here's an example involving R3. The standard basis vectors, they're denoted E1, E2, and E3, and when written as column vectors, they are 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then, as usual, the column vector 1, 0, 0 corresponds to the n tuple, in this case 3 tuple, 1, 0, 0, and similarly for E2 and E3. And then similarly, R4 has 4 standard basis vectors, E1, E2, E3, and E4. Each of these is a 4 tuple, or when expressed as a column vector, a 4 by 1 column vector with zeros in every spot except for 1. One fact about the standard basis vectors is that every vector in R3 is a sum of multiples of these standard basis vectors E1, E2, and E3. In other words, each vector is what's called a linear combination of the standard basis vectors. Here's an example. The column vector 2, 5, minus 7, that's an element of R3, in other words, a 3 tuple of real numbers. And this can be written as 2 times the first standard basis vector, 5 times the second standard basis vector E2, and negative 7 times the third standard basis vector E3. Why is that? Well, 2 times E1 is just 1, 0, 0. And when you multiply a scalar by a matrix, you multiply every single entry in the matrix by that scalar. 2 times 1 is 2, 0 times 2 is still 0, and similarly 0 times 2 is still 0 here. Ditto with 5 and minus 7, that gives rise to a 5 and minus 7 here. And then when you add matrices, the naive process works. In other words, you add them entry-wise or component-wise. So 2, 0, 0, 2 plus 0 plus 0 is 2, 0, 5, 0, those add up to 5, and 0, 0, minus 7 adds up to minus 7. So indeed, this right-hand side here adds up to this, which is equal to that. And in the case of standard basis vectors, it's quite easy to express any vector as a linear combination of standard basis vectors. Simply, the numbers in the vector correspond to the coefficients in front of the standard basis vectors. Another reason the standard basis vectors are useful is due to the following fact. So let A be any matrix, then the image of the ith standard basis vector under the transformation that's left multiplication by A is the ith column of A. In other words, multiplying A by the standard basis vector EI, that's the vector that has zeros everywhere except a 1 in row I, that will pick out the ith column of your matrix A. And why is that? Well, if you think about what matrix multiplication A times EI does, is you take the rows of A, multiply with the columns of, in this case, EI, there's only one column, and the column, the entry here will be multiplied by 0, so it's ignored. This entry here will be multiplied by that 0 and will be ignored. And then eventually, basically, the entry in column I will multiply by this 1 here in row I, and that will be the only thing that remains. So when you do this matrix multiplication, it will pick out column I of matrix A. So that's why this very often used fact that the image of the ith standard basis vector under left multiplication by A will give the ith column of A. Let's see on the next page how we can use this. Here's an example. Let W1 be given by x1 plus x3, W2 be given by x1 plus x2 plus x3, and this is an example of a matrix transformation. And the question asks to find the matrix associated to this transformation. Again, you might ask, well, how is this a transformation? Well, x1, x2, and x3 are the input numbers, and then W1, W2 are the output numbers. The question then is find the matrix associated to this transformation. And what we learned on the last page is all you have to do is plug in the standard basis vectors, and they will give you, the output will give you, the corresponding columns. So if we plug in E1, remember E1 in the case of R3 is 1, 0, 0. And so the transformation applied to 1, 0, 0 says, well, you take the first and third numbers you give me, so 1 and 0, and add them. That will give you the first number, or the W1, as the output. And then W2, the second number, is, in this particular example, the sum of the three numbers you give me. I give you 1, 0, 0, I add them all up, and I get 1. Similarly, and so I should say that means that the first column of our matrix is going to be 1, 1. And that's what we have here. Now our second column is going to be the image of E2 under the transformation. And that's computed in this line here in the same way. Doing the arithmetic, we get 0, 1, and then 1, 1 as the image of E3. And so that's our third column and second column. And so here's our answer. For the matrix associated to this transformation, it's this matrix.